Hi everyone, my name is Munjal Shah and today I will be presenting my work on the effect of wing corrugation on insect forward flight. There are millions of species of insects on Earth. They all have varying shape and size of wing and body for efficient flight, which they have obtained through evolution. Out of them, bumblebees are most interesting of all, as they can carry up to 80% of their own weight in terms of nectar and pollen, as you can see in the pictures. And they do this while escaping predators. Currently, all computational studies model insect flight through approximations of wing as smooth surfaces, while neglecting contribution of corrugation as shown in the top figure. Our current work drops that approximations and models morphologically accurate corrugated wing in forward flight of bumblebees as shown in the bottom figure. The numerical modeling of bumblebee flight is in laminar regime based on the Reynolds number, as you can see from the equation. The maximum area obtained in our current simulation is 7800, and the numerical methods employed to solve 3D laminar incompressible flow are shown on the right side. The computational domain for the flapping flight is shown in the top figure. The symmetric boundary condition shown in pink helps mimic the two-wing behavior in a 3D setup. The motion of the wing is made possible through overset meshing technique, which allows the wings to move in 3D based on the defined kinematics. The parameter associated with the flapping flights are shown on the left. The current bee model is a worker bee with approximate weight of 175 mg. The normalization of forces and pressure are shown in the formula in the slide. The video on the top right shows the full flapping cycle moment of wings. The wing moves from back, that means thorax, to the front, that means head, which is called as downstroke. And when the wing moves from front to the back, that is called an upstroke. And during the downstroke, majority of the lift production happens in the bumblebees, while during the upstroke, they get most of the thrust, i.e. the forward flight capacity. Now the current study compares a smooth wing, SW, to the corrugated wing, which we have obtained through a micro-CT scan. Now the bumblebee wing is made up of two wings, that means a forewing and a hindwing, which are connected by a hook-like structure called as hemuli. Now the current study will also explore the contribution of forewing and hindwing in the aerodynamic performance of a bumblebee. And all the models will be modeled for three-fold velocity of 1 meter per second, 2.5 and 4.5 meter per second, as well as hovering. For results, the first time history is given for all four wing models at 4.5 meter per second of highest forward velocity. Here, CW and SW are whole wing models, the CFW and SFW are four wing models. The non-dimensional time of flapping cycle is shown on x-axis. In first time history, the downstroke is from 0 to 0.5 and upstroke is from 0.5 to 1, which is shown in the shaded region. We have lift curves on the left side and the thrust curves on the right side. The lift curve shows that during the mid-downstroke, the corrugated model shows higher lift production, suggesting corrugation impacts load lifting capacity of bumblebees. During the upstroke, however, the lift curves are almost identical after the stroke reversal. This suggests that the dorsal side, that means the top side corrugation, has a major impact on aerodynamics than the bottom side, which is the ventral side. Now for the thrust, the corrugated model shows that they have higher drag compared to the smooth models. Now during the stroke reversal, we see that there is a sudden drop in lift for the forewing models in absence of the hindwing. Now for the stroke reversal, for the thrust production, we see that the forewing model shows an increase in thrust in absence of the hindwing. That means our results are suggesting that the hindwing is very important for the lift production during stroke reversal at the cost of higher drag. And because the main function of a worker bee is to carry nectar and pollen, that higher cost of drag is necessary. But in case of the forewing models or the whole wing models, the corrugation plays a very important part in increasing the load lifting capacity of bumblebees. Here figure shows vorticity at different span location at time 0.31, which is immediately after mid-stroke. The vorticity comparison between corrugated wing model and smooth wing model at 75% and 87.5% shows larger tip vortex and leading edge vortex in corrugated model because of forewing corrugation. This is the reason for higher lift in corrugated models we saw in force time history. If you compare the corrugated wing model and the corrugated forewing model, the size of tip vortex and the leading edge vortex remain the same in CFW even after the absence of hind wing, suggesting that forewing is the part of the wing responsible for the formation of tip vortex and leading edge vortex. The trap vortices between the span location 25 to 50% are caused by corrugation and the natural camber of wing, which causes more drag during the downstroke as seen earlier in the force time history. The corrugation sheds higher magnitude vortice in the wake which wing encounters during the upstroke, which causes slightly higher thrust during upstroke for corrugated models. Now let's talk about stroke reversal. Here we have shown isosurfaces of Q criterion to highlight important vortex structures in the flow. The video on the left shows the stroke reversal between time 0.47 to 0.73. Now qualitatively speaking, based on the video, the corrugated models shed more or higher magnitude vortices than smooth wing models, as you can see. Now figures on the right shows the comparison between all models at time 0.65 after the stroke reversal. Upon comparison between the model, the tip vortex shaded in the wake are stronger in corrugated models CW and CFW than compared to the SW and SFW. Comparing corrugated wing and smooth wing models, we see that the corrugation sheds dense trailing edge vortex in corrugated wing compared to the smooth wing model. The trailing edge vortex formation changes in the absence of hind wing in the last two figures as you saw. And the horseshoe-like trailing edge vortex that we saw in corrugated wing and the smooth wing is absent in CFW and SFW model, which causes lower lift and higher thrust during the stroke reversal. Let's talk about trailing edge vortex. Although we saw that the forewing matches LEV formation, the trailing edge vortex formation is drastically affected by the absence of hind wing. The pressure contours, which is shown on the right side, are at 0.47 near stroke reversal. It shows that the absence of higher pressure region on forewing models because there is no surface for flow to be attached upon reversal. Hence, the flow encounters minimal hindrance from the wing. The comparison on the bottom is for the forewing models after the stroke reversal. It shows that the isosurfaces of Q criterion to highlight the dense trailing edge vortex in the flow. We see that instead of horseshoe-like trailing edge vortex, we have cylindrically shaped trailing edge vortex because of the long trailing edge in the forewing models. The cyclic average value of lift for corrugated wing and smooth wing model is shown in the table on the right, with the forward velocity of 1, 2.5 and 4.5 meter per second. The qualitative comparison between corrugated model and smooth models with respect to the body weight of bumblebee is shown in the figure on the left. The solid lines show the comparison between the corrugated wing model and the smooth wing model. We see that the lift enhancement due to the corrugation reaches up to 15% at 4.5 meter per second of highest velocity. The contribution of corrugation also increases with the forward velocity. The dashed lines shows the comparison between the corrugated wing model and the corrugated forewing model. We see that the forewing contributes up to 60% of the lift production. But as the load lifting capacity of the bumblebee are more important for worker bees, the hindwing becomes essential as it contributes the rest of the 40%. The hindwing contribution also increases with increase in velocity. We see that the lower velocity at a lower velocity of 1 meter per second, the forewing contribution is up to 85%. That means the forewing can match up to 85% of lead production on its own in absence of hindwing at lower velocity. In conclusion, we see that the corrugation enhances the strength of leading edge vortex and tip vortex. We also saw that the corrugation contributes to nectar and pollen carrying capacity of bumblebees based on the force time history. Forewing contribution, the forewing corrugation contribution can generate leading edge vortex and tip vortex of equal strength as whole wing models. And we also saw that the hind wings are a necessary part of wing morphology as they contribute up to 40% of the lift production at forward velocity of 4.5 meter per second. Also, the differences in force production between corrugated models and the smooth models provide strong evidence for inclusion of corrugation in future studies. The current study highlights the unexplored area of insect aerodynamics and provides evidence that the smooth wing approximation in simulations do not account for unsteady changes in flow due to morphology of bumblebees. This work was performed in part at Center for Computational Research at University of Buffalo. We would also like to thank School of Engineering and Applied Sciences at University of Buffalo for their financial support. Thank you. If you have any questions, I am happy to answer them now.